G'day, and thanks for stopping by at the eCave. In this episode, which is part one of two parts, I'll be talking about my experience with 3.5-inch diskette drives. If you're interested in that, why not join me in eCave? Well, thanks for staying. In this first episode, I will share with you some of my learnings while testing a fair few 3.5-inch diskette drives. The stack here on the left is 1.44 megabytes, and this is my only 720K diskette drive, but I'll talk a bit more about that later. Now, what I will be going into in a bit of detail is the interface, that is, the floppy controller to diskette drive interface. I'm not going to be giving you a rundown on how a diskette is written to or read from. I'm sure there are plenty other videos or tutorials on that. So this is primarily focused on the interface itself. Now, a couple of more things. I've always been interested in finding out or trying to work out how the PC BIOS detects a diskette drive which is attached to the controller on the motherboard. So that's something we will find out and I'll tell you about. The second thing we'll look into is when a diskette drive is detected, how does the floppy controller or the BIOS determine whether it's a 1.44 megabyte diskette drive or a 720K one? So we'll get to that towards the end. I've been using my IBM PC 300GL, which is a Pentium machine. It dates from April 1987. It has both an ISA and a PCI bus expansion slot, and it does support 2 diskette drives. So that's the one I've been using to test all of these. The PC 300GL is a pretty much stock standard industry implementation of the 3.5-inch diskette drive interface. So all the things I'm talking about here would apply to other generic desktops or PCs. Now in the second episode, I'll be talking about the PS2 Model 30 to a 6 diskette interface and the differences from the standard. Now these machines predate pretty much the PC 300 by about 10 years. So when IBM implemented that diskette drive interface, they chose to do something different. So in the second episode, I'll talk about that. Anyway, it's time to get stuck into the diskette drive interface. So I'll run you through how it works or what the lines are used for. So let's get started with that. As you see here on the left side, we have the computer. And on the right side is a diskette drive. The critical thing to understand with diskette drives, they're just slaves. They have no CPU or a processor on board. Everything is controlled by the floppy disk controller, which is a CPU in its own right. And it hooks up to the PC bus, and obviously the BIOS and the DOS routines running interact with it. Between the diskette controller and the diskette drive, you have a number of lines, i.e. signal lines. They're broadly split into 3 categories: control lines, data lines, and sense lines. The control lines go from the floppy disk controller to the diskette drive. The data lines go both ways, given the fact that we are writing and reading data. to a diskette, and the sense lines go from the diskette drive to the floppy controller. Now, let's look at the cable interface. The cable basically is a 34-pin IDC cable, and if you look at the pinout, you have the 34 pins numbered from 1 to 34. But one side of the pinout is all the odd numbers, and the other side is all the even numbers. For most 3.5-inch diskette drives, all the odd numbered wires are ground, but there are some exceptions. I'll talk about that later when I talk about the IBM diskette interface. Whereas all the control data and sense lines are even numbers. Now, when you look at the control lines, which we'll talk about here first, they are the ones that actually select the diskette drive and start the motor. For most floppy disk controllers, you can have two drives, A and B. Therefore, you have a drive select 0 and drive select 1. And then you have motor enable 0 and motor enable 1. Now, what happens when you do a drive select and motor enable, the spindle motor in the diskette drive starts turning. Now, in the early days of diskette drives, these were separate signals. You could actually start the motor without having drive select, but nowadays drive select 0 and motor enable are usually tied together. So when you select drive 0, which is drive A, the spindle motor starts running automatically. The next control lines we have are the direction, step, ride, gate enable, and head select. The first step is obviously to start or do a device select and start the motor turning. The direction tells the drive whether to step the head towards cylinder 0, which is on the outside of the diskette, or towards cylinder 80, which is on the inside of the diskette. Step tells the stepper motor that controls the head to move in either direction, depending on signal 18. So it will either go from 0 up to 80, or go from 80 down to 0, and anywhere in between. Now, another signal here, head select, because these are double density drives. There's a head on top of the diskette, and there's another head underside. The underside is head 0, and the top side is head 1. And signal or control line 32 tells the drive which head to activate. Control line 24, ride, gate, enable. It's either called ride gate or ride enable. It's basically a mechanism to tell the diskette drive to switch between reading or writing on the diskette, because the heads are used for both. And if you want to read from the diskette, you have to have it in read mode, all the logic in the diskette, or if you want to write, you have to have it in write mode, and thus control line does that. Next, we have the data lines. They're fairly straightforward. On one side you have write data, which flows across to the diskette drive. On the other side, when you're reading data from diskette, you have read data coming back to the diskette controller. Next, we have the sense lines. These are the lines that are all the signals sent from the diskette drive to the floppy disk controller to indicate certain things. The most obvious one is index pulse. When the drive has been selected and the spindle motor is turning, for every circle the diskette turns, an index pulse is sent back to the floppy controller. This tells the floppy controller where the sector starts on that particular track. The next signal, track 0, tells the floppy controller that the head is on track 0, which is the outermost track on the diskette. Another signal which comes from these holes in the diskette is the write protect signal. So if you write protect the diskette, it blocks the hole and activates a little micro switch, and that micro switch sends a write protect signal to the floppy disk controller that prevents it from writing onto the diskette if you then try to do that. There's another little micro switch here called diskette change. It's important for the floppy disk controller to understand that if you're working on the diskette, loading programs from it and running programs from the diskette, if you then remove the diskette and put a different diskette in, it needs to know, and that's what this thing is, simply another micro switch here that detects that the diskette has been taken out and another one put in, and it's a signal sent to the controller. Fairly straightforward. And lastly, we have power. Basically, plus 5 volts and plus 12 volts are delivered to the drive to power the logic. Now, the 5 volt power the IC circuits and the TTL logic used for the sending of sense lines and data back to the floppy disk controller. Now, the 12 volts are used for the stepper motors, although in most 3.5-inch diskette drives nowadays, the stepper motor actually to run from the 5 volts, so the 12 volts may not even be required. But for the old drives, it would have been required. The next thing to understand are the signal levels on the lines. They are range from 0 volts to 5 volts. So when the computer and the floppy disk controller are powered on, all the lines here, signal lines, go to 5 volts. And then if a control line is activated by the floppy disk controller, it's done by pulling that 5 volt control line down to 0. So that's what this represents. So if you have an active signal, it goes down to 0. And that's what the diskette drive or the floppy disk controller act on. When the 5 volts go down to 0, that means that signal line has been activated. You can see here a logic analyzer trace of a diskette being booted up on a PC 300GL, which is the IBM PC. And you can see as soon as the drive and the PC is powered on, all the signals lines go high, i.e. to 5 volts. And then, as part of the boot up process, the floppy disk controller does a drive select 0. You can see that going active down here, and at the same time, the motor on goes active as well. The direction is high, and the step pulses are sent to the drive. That causes the stepper motor spindle driving the head to move the head towards track 0 until a track 0 signal is generated. Now, I'm not going to go into more detail on this, but this is sort of an overview of how the diskette drive is actually sensed, but I'll talk a bit more about that. Now, another critical piece of information in relation to the interface are the pull-up resistors. For proper signal levels, you need pull-up resistors to the plus 5 volts, and this is where the resistors are connected from plus 5 volt to the signal line, and it is on both sides, so both on the diskette drive and the floppy disk controller. This will become more important as we talk about that a bit later, but the original sugar standard talked about 150 ohms up to 10 kilo ohms. What appears to have occurred over time is, I think most 3.5-inch diskette drives nowadays have 1 kilo ohm. But you can easily calculate what the current is based on the pull-up resistor. And I've given some indicative resistor values plus the current. What's important to know here is some circuits, i.e. in the diskette controller, when it's pulling the control lines down, they are not going to tolerate 33.3 milliamps. I think at best you're looking at 5 milliamps tolerance for most TTL logic in the diskette controller. Now, I've actually measured the pull-up resistance in the IBM PC 300GL, and as you can see, for the control signal lines coming into the floppy disk controller, or the sense lines, the pull-up resistor is 1 kilo ohm. On the other hand, for the control lines going back to the diskette drives pull-up resistors seem to be 1 kilo ohm, which appears to be the most common pull-up resistor in most of the 3.5-inch diskette drives I have. So that gives you an idea of the signal interface. Okay, let me show you the current draw on the control lines. Here I've got the PC 300GL, the IBM machine, with a single 3.5-inch diskette drive with, of course, a diskette in there. Yeah, that's my breakout box, or so to speak. I've actually broken into control line 32, which is the head select, or sometimes called side select. But anyway, what you see here is we have 5 volts on that control line. And this is the current draw. It is 0.004 milliamps. So basically, bugger all. Now what I've done, I've put up IMD. And with IMD, we will do an analyze. And that will allow us to switch between the sides, or head 0 and head 1. So once the analyze starts, we're on head 0, and the control line is still on 5 volts, and the current draw is 0.08 milliamps. So slightly more than before, but not much. Now watch what happens when I change to side 1, or head 1. The control line will go active and pull the 5 volts down, and you'll then see the extra current that is drawn. So I'll do it now. Okay. The control line's gone down to 0.2 volts, and now we are drawing 4.9 milliamps through the pull-up resistor. So this is how pull-up resistors influence the current draw. In this case, we have a 1K pull-up resistor, and that results in about 5 milliamps. So here's the 300GL doing IMD on a diskette with heads 0 and drive select pin 12. And while it's active, i.e. low, we're drawing 5 milliamps. So if I stop it, and it's not selected anymore, we drop down to just 0.04 milliamps. Well, now that you know about the pull-up resistors, it's time to find out how the BIOS on the motherboard detects a diskette drive attached to the interface. Or if there's no drive attached to the interface, how would the BIOS know that? Now, in my previous overview on the interface, I showed you the logic analyzer trace on the diskette interface for the PC300GL booting into DOS with a diskette drive. As you could see, the BIOS first does a select drive 0 control line plus the motor 0 enable control line. This actually starts the spindle turning on the diskette drive, plus you see the activity lights. It then sends stepper motor pulses on the step line. Now, because the direction control line is high, the stepper motor will drive the head towards the home position, which is track 0. And this is where most 3.5-inch diskette drives have a track 0 sensor. And as soon as the track 0 sensor detects the head in the home position, it sends out a signal on the sense line, a pulse, a track 0 pulse. When the BIOS sees the track 0 pulse, it now knows that a diskette drive is attached to the interface. So it proceeds to do the device select 1 and motor enable 1 to do the same thing for the second drive, i.e. a B drive. So if the sensor track 0 doesn't send a pulse after the activation of the drive plus the stepper motor pulses, the BIOS won't see the drive. Now, the other thing I've discovered is that once the BIOS detects the drive, it obviously generates a configuration error, and you have to go into the BIOS to confirm and save that configuration change. But what the BIOS doesn't know is the density of the diskette drive. It simply assumes it's a 1.44 megabyte density diskette drive. So it's up to you to make the right choices. Thankfully, most 3.5-inch diskette drives are 1.44 megabytes, so that's not a problem. So let me first show you how the PC300GL complains with a configuration error when you attach a diskette drive to it for the first time, or if it hasn't got any diskette drive configured. Now here we have the PC300, and I've disconnected the only diskette drive attached to it. And according to the config, there is no diskette drive attached. So what I'll do, I will reattach the diskette drive and power it on and show you what happens, because the BIOS will detect the diskette drive. Okay, the diskette drive is now connected again. And let's power on and see what happens. The diskette drive will be sensed by the BIOS, and it should generate a config error. So let's wait for that. There it is, and we have to go and do F1 to go into the configuration, which allows us to validate and save the configuration for a single diskette drive. Now, as you will probably see in the configuration, the drive that's been detected is the A drive, and the BIOS reckons is a 1.44 megabyte, 3.5-inch drive. So, but that's just pure speculation on the BIOS's half. The only thing it has detected is a diskette drive. There's no control lines telling the BIOS which type of drive this is. As you saw in the configuration, the BIOS had detected the drive as 1.44 megabyte. Now, to double check that, I pulled out one of the 720K diskette drives from my IBM PC JX, which I've talked about before. This actual drive probably dates from 1984, so it's a lot older than the diskette drives here, which is probably late 90s, early 2000s. However, it has the same interface as these, so exactly pin accurate interface, same as a standard 3.5-inch. So I could plug that into the PC300GO and see if it detects it. And of course, that's exactly what it did. And guess what? It assigned a 1.44 megabyte configuration to it automatically, which obviously tells me is simply guessing that. Now, I could see in the configuration it doesn't support 720K. However, I was using IMD, which is the DOS software from David Dunfield, which allows you to create or read images of diskettes, but also analyze the track alignment. So I used IMD to set up the proper configuration for a 720K drive, which is essentially just dropping the number of tracks from 80 to 40. And it happily read the 720K diskette drive. And I think it's simply a BIOS configuration missing for a 720K drive within the PC300 BIOS, and that's why it doesn't support it. All right, I've hooked up the 720K diskette drive. This is I think it's a Panasonic one, fairly old one, and it's simply not capable of 1.44K. It's only 720K. It actually comes from the IBM PC JX, which I've talked about and shown before. So let's start up the PC and see if it doesn't detect the diskette drive. Yeah, diskette configuration drive error. We'll have to go to configuration. And let's see what the configuration says. We go to devices, and there you have it. It thinks the 720K drive is a 1.44 megabyte drive. And sadly, the BIOS doesn't even support 720Ks. The other thing I did was to confirm the sensing of the diskette drive. And how do we do that? Well, it's simple. We attach a diskette drive to the interface, but the only thing I will disable is pin 26, which is the track 0 signal line back to the floppy controller. So let's see what happens when we do that. So the PC300 has a configured 144 megabyte diskette drive, so that's all working fine. It's turned off, and what I've done is, as you see here, disconnected pin 26. Pin 26 is the track 0 signal from the diskette drive to the floppy controller on board the PC. So when we turn on and it boots, it will suddenly detect that there is no diskette drive. So, see here. So without the track 0 signal, it can't detect the diskette drive. Well, there you have it. If you attach a diskette drive to your PC and you see the activity light and the spindle turning, but the diskette drive is not detected by your BIOS, well, now you know what's happening. The track 0 pulse is not getting back to the floppy controller. Now this could be a variety of reasons, but most commonly it would probably be the head being stuck, so the stepper motor can't turn it back to the home position, or the stepper motor becomes so stiff the same thing occurs. Now this means you can better understand some of the problems you'll have with diskette drive, I hope. And this has given you some insight into how the 3.5-inch diskette drives actually are detected, and also the fact that you have to manually configure the density of the drive if it, for whatever reason, is incorrect. Now, I'll put a link to Dave Dunfield's IMD DOS software. It's a fantastic piece of software, especially if you're tinkering with diskette drives, regardless of their size, whether they're 8-inch, 5.25, or 3.5-inch. This software will give you a lot of insight into how the drive works, or actually some of the errors you can see from the drive. But anyway, I hope this has been interesting for you. So look out for episode 2, where I'll talk a bit more about the IBM proprietary interface for the PS2 Model 3286 and how it differs from the industry standard, like on the PC300 and GL. So, thanks for coming into the eCave. Until next time, see you then.